energy. So this is E squared minus E that's in here. Okay, so what is this? When you look at these, Michael, what do you think? You got. Let's just look at the first one. P squared equals m squared.
Right.
That's the same as saying, well, p squared is e squared minus p dot p equals m squared. And now, since e squared minus p squared, so you know,
e squared minus p squared equals m squared, so
m squared c to the fourth. So if I throw some c's in there,
yeah, so throw some c's in there, then you get m squared c to the fourth. Yeah, I've seen this.
p squared,
this is what you were wanting to get to. Yeah.
Okay, plus m squared c to the fourth, and there's another c squared, p squared c squared.
P squared c squared.
This is it.
Plus m squared c to the fourth. That's it.
This is a big relation.
That's the energy equation in high energy particle physics. That's
okay. These things, these are come from the orbits of this group. This is where they originate. The orbits are. Let me draw my. Okay, this is going to be P1. Really, no, I'm in the dual space, so I get to write it like this: P1, P2, and P0. This is the time dimension, usually. Okay, so what I get is that picture that I had over here. Okay, and then the cone. And then there's something that comes out the bottom here, that's the other half. Okay, here's what this is. Xm plus is when P naught is greater than 0, so I'm in the upper half plane, and P squared equals m squared. So this is Xm plus here. This is an orbit. If you're in the, so what this means is, if I'm an observer in my laboratory, and I measure your coordinates to be somewhere on this shell, if I do any old Lorentz transformation that's in these groups, okay, that preserves time. So I want to get another perspective. I transform to another laboratory's perspective. I end up on that shell. These are called mass shells. All right. C is the speed of light. Yeah. Sorry, Catherine. I'm going back and forth between physics and math, and so just to ask if there's some physics that's unfamiliar.
2 minutes.
Oh, I went way over, didn't I? Okay, so I always do this. So these are the forward and backward light cones. This is, if I just look at this, this is Xm minus. The m goes down here. Minus. This is y, m, and then I've got this point 0. Okay, so these shapes are my orbits. And this is called the, Xm can be 0, remember I said that? So this is actually x0 plus that forward light cone, that's what it's called, forward light cone. This is, right here, that is x0 minus, and that's the backward light cone. Okay, and what this does is preserve causality. If I'm within the Xm minus range, I can't escape this light cone boundary, or I get outside of sort of where it's possible for me to go. There's no way you can change perspectives. There's no way you can transform coordinates and end up outside of there. You're stuck on this orbit, actually. So you're just going to move around in that half of the hyperbola. That's the only place your coordinates can be. Okay. This is really, that's it. That's the punchline. I wanted to show that picture, and hopefully you'll see the orbits and what the mass shells mean. You've probably heard the phrase on mass shell. And so that's related to this right here. This is what they're talking about. Any questions?
I want to digest this for a little while before I know how to ask questions. I think I got the idea.
That's really what I'm hoping you get from this too, and you can go back
I
and
need to work
notes.
with it some.
But you kind of get this feeling of, if nothing else, whoa, all this highfalutin math is really applied, and it really, this is my sentiment at least, that if we, to get at the heart of physics, it's important to understand this math right here. We can philosophize, we can talk in general terms, but to really understand what's going on in real